In this kinematics problem, we're going to be looking at a good problem that has the opportunity for us to investigate a qualitative reasoning and quantitative reasoning. This is a problem in which a person is standing in the basket of a hot air balloon, and that person is holding a rock of negligible mass directly over the edge of the basket, top edge of the basket of the balloon, such that when the person lets go of the rock, it will fall freely straight down towards the ground, and it won't hit anything until it hits the ground. Alright, so he's holding it over the edge of this basket attached to the hot air balloon. The hot air balloon is accelerating upwards at a constant rate, and that's going to be a rate of positive 2.0 meters per second squared. So we'll call up positive. At the instant when the hot air balloon reaches an upward velocity of 3.0 meters per second, that person is going to release his grip on the rock so that it can just fall freely straight downward. A stationary observer on the ground is watching this happen from some convenient vantage point, and we're also going to think about what the person who is a stationary observer on the ground is going to see. So we're going to assume free fall conditions, meaning gravity is the only force acting on these objects, and that's going to accelerate them at a constant rate. We'll call it 10 meters per second squared downward. And we have a quantitative question: determine how long it takes for the rock to pass the bottom of the basket. Assume the basket is 1.5 meters in height. And we also have a qualitative set of questions. One, or part A, what does the person in the basket see upon releasing the rock? Basically, what does it look like when the rock is released to the person standing in the basket? And then part B, what does it look like to the observer on the ground? So sometimes choosing to begin kind of with a qualitative or conceptual assessment of the situation helps you deal with the quantitative question. For some people, starting with the quantitative question helps them be able to go back and answer the conceptual or more qualitative aspects of a question. So they both are going to go hand in hand and need to be able to make sense together. But sometimes it's more helpful to start with one than the other. I'm going to start by looking at the qualitative question of part A, and that's asking, what does it look like, what does the rock look like to the person in the basket when he or she lets go? I'm drawing a little picture here just to give me some orientation and kind of write down what I know. I know once the rock is released, it's going to have a downward acceleration of g, which we're actually calling 10 meters per second squared downward in this example for simplicity. I have an upward velocity of the balloon and the rock and the person, everybody in that system of particles, balloon, rock, person, they have an initial upward velocity of 3 meters per second, because that's what we're told is the initial upward velocity at the moment the rock is released. The acceleration of the balloon is also given as plus 2 meters per second squared, so I've written that in as well. I got my little person who's an observer on the bottom right, standing on the ground, and I also have a magnification now of the person in the basket in my bottom left of my drawing. And this is what it looks like for the person in the basket. This person in the basket is holding the rock, and from his or her perspective, that rock starts with 0 velocity. Right? He's moving upward with 3 meters per second. The rock is moving upward at 3 meters per second. The balloon is moving upward at 3 meters per second. And at that moment, there they all have the same velocity, and so when he releases the rock, it looks to him like he's releasing it from rest. So I drew it a few times there, T0, T1, T2, T3. So to the person in the basket, it looks like the rock is just in free fall, but it doesn't just have an acceleration g, since he or she in the basket, as well as the whole balloon and the balloon basket, are still accelerating upward at positive 2 meters per second squared. The rock to the person in the basket seems to have an acceleration downward that is g plus that extra acceleration upward. And that's the acceleration of the rock from the person's perspective. It looks like it has an extra bit of acceleration. Okay? And this actually translates into some apparent artificial gravity, like if you're in an elevator and the elevator is accelerating upward, you actually feel a little bit heavier when the elevator is accelerating upward. And indeed, if you take a bathroom scale in there with you the next time you're in an elevator, see if you can record in slow motion how that scale reading changes when the elevator starts to accelerate, and during that acceleration upward, just when it's changing its velocity upward, you actually experience a heavier weight, a greater force downward. And that's directly related to this acceleration value. It seems like the rock to the person in the balloon basket is actually accelerating towards the ground faster than g, or at a faster rate than g. In fact, it's g plus that acceleration of the balloon upwards. So that would actually be a value of minus 12 meters per second squared. Alright, so that's kind of a good conceptual answer to part A. It appears for the person in the basket, since he's already moving upwards with the rock initially, that they begin at the same velocity at rest in relation to the basket, and it seems that the rock accelerates downward past the edge of the basket, beginning from rest with a value of an acceleration that is slightly greater than g. Now for the person who's over there on the stationary observing this thing from the ground, I have down in the bottom right what he seems to see, which is that the person releases the ball, or the rock rather, and both continue to move upward. The balloon is continuing to accelerate upward, so it's speeding up in the upward direction. The ball, now having been released, is still moving upward because it has an initial velocity of 3 meters per second from the observer on the ground's perspective. And that ball, after being released, it continues to move upward for a moment with 3 meters per second as a velocity, but now that it is no longer attached to the balloon person rock system, it's no longer part of the accelerating upward balloon, it actually has a net acceleration that's just equal to g downward. So that ball, or rock again rather, starts to slow down, comes to a stop at t3 that I've drawn, and then at t4, t5, t6, t7, it's accelerating and speeding up downward now. So it kind of looks like the rock has this shaped trajectory. It moves up for a bit, comes to a stop as if it had just been thrown upward because it was already moving up with a velocity of 3 meters per second. And then the observer on the ground sees it reach its maximum height, come to a stop, and then start speeding up downwards. So it looks different for the person who is observing this. Also, while the person on the ground observing the ball do this, he's also seeing the accelerated upward motion of the basket and the person in the balloon. So the rock appears to continue to travel upwards for a short time before coming to a stop for an instant, according to the person standing on the ground observing. Then the rock picks up speed and falls towards the ground there. Now, in order to answer our quantitative question, we can think about it a couple ways. The simplest and easiest way is to think of it from the person in the balloon basket's perspective, because we could use our kinematic equation now that there is some displacement of the rock relative to the basket. It's going to move that 1.5 meters, that is the height of the basket, and we want to know how much time it takes for that accelerating rock to reach the bottom of the basket, 1.5 meters below its initial starting point. From the perspective of the person in the basket, that rock has an initial velocity of 0, and it's accelerating with the downward acceleration that is actually greater than g. So it's that same kinematic equation of delta y, which is going to be that minus 1.5 meters, equals the initial velocity in the y direction times time. Well, from the person in the basket's perspective, that initial velocity is 0, so v0 yt is equal to 0. And then minus 1/2 gt squared, it's not g, it's rather the acceleration from the basket moving upward, that magnitude plus g, because it appears that it's actually accelerating at a greater rate from the person in the basket's perspective. So it's 0 minus 1/2 the acceleration of the rock from that person's perspective now, slightly greater than g, times time squared. And so we're looking for that t squared value. Right now I have it written out under that radical. I have that 1.5 meters times 2, because I've solved for t, divided by the acceleration of the rock, which is equal to the acceleration due to gravity plus that magnitude of acceleration from the hot air balloon moving upwards. So that added together is 10 meters per second squared from g plus the 2 meters per second squared from the acceleration of the balloon, or the hot air balloon. That's going to give us a value that is the square root of 1/4, which of course is equal to 1/2 seconds, or 0.5 seconds. That's how much time it should take for that rock after being released to pass the bottom of the basket. Now it's a slightly different perspective from the person on the ground, right? Like the person on the ground is actually seeing two different motions happening at the same time. So the next slide that we'll look at is just going to have again what we have from before. We'll skip ahead from the whole question. There's our results from that quantitative question of how much time it should take for the ball, or the rock, I keep calling it a ball, the rock and the bottom of the basket to pass one another. I got my image or drawing from before the situation in the bottom left, and then the perspective of the individual on the ground there straight at the bottom. So now we're going to analyze the situation. If you don't quite believe that the perceived acceleration of the rock according to the person in the basket is g plus the upward acceleration of the basket, then we'll go through a more thorough analytical evaluation or assessment of the situation from the observer on the ground's perspective. So this is now an answer to this quantitative question 1, but from part B, from the perspective of the person on the ground. That person observes two separate motions, that of the balloon, which has an acceleration, initial velocity, and an initial position, and the motion of the rock, which also has an acceleration just at the moment, and following release of the rock by the person, it has a different acceleration. It has an initial velocity, and it has its own initial position to start with. And say all these are at some given time t0. I'll draw an initial position schematic over there in the top right that shows the top of the basket and the bottom of the basket, where the bottom of the basket is the 0 position, and the top is 1.5 meters. That's the height of the basket. The rock starts there at the top at a position that is 1.5 meters above the 0 line. The final position of both these objects is going to be somewhere where the bottom of the basket and the rock are on that same line, because that's the position where that's in the question. How long does it take for them to be at that spot, for the rock and the bottom of the basket to occupy the same position vertically? I can write in some stuff that I know. I know the acceleration of the balloon is plus 2 meters per second squared upwards. Its initial velocity is plus 3 meters per second. I know that the acceleration of the rock, now this is, t0 is when the rock is released. So now having been released, the rock has an acceleration that is just g. It's in free fall. It's no longer being accelerated upward by the hot air balloon. So it has an acceleration that is equal to g. It has an initial velocity that is also plus 3 meters per second, because it's observer on the ground, as we said, and as we have depicted in the bottom diagram, the observer on the ground sees it after the moment it's released, still having an initial velocity upwards of 3 meters per second, because it was moving and traveling with the hot air balloon and the person. And it has some initial, the initial positions we'll identify now for the balloon and the rock. On the bottom right side, or the mid-right side area of my screen, I have now what it'll look like when the rock and the basket occupy that same final position, where they have the rock and the bottom of the basket in the same spot. And we don't know exactly where that's going to be in relation to our top diagram. We don't know if it's going to be somewhere in between the 1.5 meter and the 0 line, or somewhere else other than where I've drawn it. We do know that the basket's going to be continually accelerating upward, and the rock will have fallen some distance, and we know it's going to appear to go up a little bit and then start speeding up back down towards the ground. And at some point, we're saying that the final position is going to be somewhere here, and it may not necessarily be on our 0 line or our 1.5 meter line from the initial sketch. But we do know that they are going to occupy the same final position. That's something we do know, and that's what I've put in that box in green there. And so I'm going to write that in as a known value now in my little chart of known values, that the final position of the balloon and the final position of the rock are going to be equal. Now, from my initial position sketch up at the top right, I filled those in saying, okay, then the initial position of the balloon, that's the bottom of the basket there, that's going to be at the 0 line, and therefore the initial position of the rock is going to be at the 1.5 meter line. Their final positions will be equal. And now we can set up something where we can start to solve. First, I have the kinematic equation I'm interested in using. That's my change in vertical position is equal to initial velocity in the y direction times time, plus or minus 1/2 the acceleration times time squared. So if the thing has an acceleration equal to g and it's directed downward, then it's the minus 1/2 gt squared. If it has rockets attached to the bottom of it and it has a positive upward acceleration, then it's going to be a plus 1/2 acceleration due to the rockets times time squared. In this case, we have an acceleration due to the hot air balloon's propulsion system. So it's going to have a plus 1/2 acceleration of the balloon times time squared. Could be in there. Okay. Remember that the minus 1/2 g part, that's if the conditions are free fall. So we only have that for one of our motions, that of the rock. I'm going to write out these, given that I can substitute some stuff in there. I have the recall delta y means y final minus y initial, just a change in the y position. So I've written out in the next equation below that in now my purple box. The y final position, the final y position of the balloon is equal to the initial position of the balloon plus its initial velocity of the balloon times time plus 1/2 acceleration of the balloon times time squared. I've just substituted in my subscripts for the balloon to keep track of stuff, and I have the same equation that I'm going to use for the rock. I have the final position of the rock equals the initial position of the rock plus the initial velocity of the rock times time. Now, since the rock's in free fall, it'll be minus 1/2 gt squared. Again, I'm calling down negative. Now, these, we said, are going to have the same final position. So those two equations are going to be equal to one another. They're both equal to the same thing, so they can be set equal to one another. So there I have them set out. I've just copied over each one that I've underlined. They're now equal to each other and on either side of the equation of my equal sign underspectively. You can see that they're in the underlined purple and pink portions. I then make the next observation that my initial velocities of plus 3 meters per second are the same for both. So those portions of the equations that I'll show you now that are v naught bt and v naught rt, those are actually equal to one another because those are the same velocities. I can subtract one of those from both sides, and that just gets rid of both of them because they have the same value. T is the thing I'm looking for, so I want to try to isolate my variable t, and I'm going to do that by adding 1/2 gt squared to both sides, and I'm also in the same motion going to subtract y naught b, the initial velocity of the balloon, just to get those positions on the same side. So now I have this left side that indicates some relationship between the accelerations and my times, and that being said equal to some change in positions. I'm going to simplify now. I noticed some common terms. My 1/2 t's are common, so I'm going to pull those or factor those out. So I have 1/2 t squared, open parentheses, g plus a sub b, close parentheses, equals, these change in positions. You can go back to my chart up at the top and see that y naught r minus y naught b is actually equal to just 1.5 meters. The initial position of the rock is 1.5 meters on my initial position chart up there, minus the initial position of the balloon, which we said, or really the basket, the bottom of the basket, is 0, so that that difference is 1.5 meters. I'm solving for t squared now, so I have t squared equals twice 1.5 meters divided by the sum of the accelerations there, which equals the square root of 3 over 12, or 3 meters over 12 meters per second squared. We'll see our meters cancel out. We get seconds squared. So we have the square root of 1 over 4 seconds squared, which is equal to 1/2 seconds, which is 0.5 seconds, which if you go back over to the top left, that's exactly what we got in the much faster way of analyzing the problem. Now we have just the full view of the entire analysis of it from the perspective of the person on the ground. So, a couple things here. One, there's usually a lot faster way to solve problems like this just by changing your perspective. So if we are in the perspective of the person in the actual basket of the balloon and think about what it looks like for that person to view this rock falling, it's real quick to solve the problem so long as we recognize that we actually have an extra large acceleration that the rock appears to have, g plus the acceleration upward of the hot air balloon. If we don't have that perspective, we actually have the perspective of the person on the ground, then we have to do the analysis of both the motions and figure out where they meet, where the bottom of the basket and the rock have the same final position. And again, in doing so, we select the appropriate kinematic equation. In this case, I've decided to set them equal to one another since they share the same final position. Evaluate that, find a solution for the time, and we can see that it matches up with our quicker solution from the perspective of the person standing in the basket.